Hej.
Jeg glemte sgu at uploade på kampen, og har lige gjort den nu.
Det er okay. Nej.
Det er ikke noget problem.
Det havde været den anden vej rundt.
Det er
Fordi peer grade lukker skarpt.
Ja.
Det kan Campusnet ikke.
Nej, det var bare mere, at der står stadig, det var for sent uploadet.
Hvis nu jeg har været så dum og ikke afleveret papirkort, men kan få Campusnet, kan jeg så nå at aflevere stadig?
Yeah, I'm like that too.
So, good morning. I just had a couple of questions just right now regarding what if I forgot to upload in CampusNet or in PeerGrade or something like that. So in CampusNet, the assignment is still open, so there's no problem if you need to upload there. In PeerGrade, you cannot hand in after the due date, but I will open it again in the break so that just to everyone so you can hand it in within the next hour or so. For those of you who have problems or challenges, are there any other, you can say, issues in that regard? Yes?
Regarding the student number,
That's fine, as long as I can decode whom it is. But you do have initials.
yeah.
So your initials, you can say, are effectively the same as a study number. But that's the way, I mean, that's my login as well. So it's kind of the login to the system.
But it's just written on the report, not on the
No, you're not allowed to do that. No, you're not allowed to do that. Yeah, we can discuss that later. Another question? You were only allowed to upload one combined PDF file. Yes, but for the PeerGrade system, since I wanted everyone to be able to just download a PDF whenever you're going to PeerGrade, I said that you're only allowed to upload one PDF, because all of a sudden when you allow a lot of different files, my own experience is that there's someone who cannot open it. And if someone cannot open something that you've made, how should you grade that? So therefore, I set the PeerGrade system to only upload PDF. If you need help to kind of combine everything into one PDF and upload it again, we'll work that out. Other questions? Does not seem to be the case. So the peer grading system, I set that to open at 10 today, just so that it opens while you're here. You do not have to spend time doing it. I will probably send out a reminder sometime next week saying that you still have time to do so, but we'll see how that works out. And take it as it comes. So for today, we will, you can say, to some extent continue on the stochastic processes. Last week we just defined the backward shift and forward shift operator that we're going to be using a lot today. And we're going to start with, you see, just a general description of stochastic processes. Then we'll come to one of the essential parts, the moving average, autoregressive, and so-called ARMA models. And we'll also talk a little bit about non-stationary models, what data, what to do. And finally, you can say, what I think is one of the more important things is how to predict. In particular, because as you've done today in the assignment, you need to do some one-step predictions in order to figure out which parameters to use. And that will be similar within this scope here. So, in general, a stochastic process is a function. It's a function of time, and it's a function of the realization. So, this is one of the mind-boggling things here. What you often see is that you have some process, you have some time, and you have some state, and then what you will observe is just something. But that's not the stochastic process, because this one is just one realization of it. So this is one small omega. Let's call this one omega 1. But we could have another realization that does something different. Let's call that omega 2. And I got a third color here. So let's just do something that does something different down here. So if I look at this, if I made an experiment, for instance, I would only get one realization. So I would get, say, one of these or something totally different. Most likely something totally different. But you only get one, usually. So you have, somehow you can choose which times are allowed, and somehow you choose your sample space. Typically in this course, we will have a sample space that is R. Just take any real number. That also means that if I look at a particular point in time, t0, what do I get? Well, there I have all the realizations possible. So what I get is somehow a distribution of what are the possible, how likely is it to get a realization here, there, and so forth. So I have a density across my state space for any given point in time. Think of it as a normal distribution. If you have, say, the most simple process we can make is just some white noise, that means it's just a sequence of random numbers. If you do that many times and look at the 10th number in that sequence, well, you got a sequence, you have a list of IID standard normals. So you have a density like that. And yes, if you take x of omega, then you get a particular realization. And as I said, that's what we often have. And we'll just denote them as xt because we observed them at that point in time. So we have lowercase x, as we discussed earlier, that's when we observed it. And in this course, we will consider discrete time, and we'll be, you can say, in the real numbers. Of course, we can make transformations so that we are in a subspace of the real numbers. Say, if you take the exponential of a real, well, then you are in the positive numbers, and you can do other transformations, if you like, to be in certain parts. But the underlying processes that we will consider are living on the real numbers. This is basically just the same plot here. So, what characterizes such a stochastic process? Well, we said that we'll kind of restrict ourselves to be in discrete time. But you can say it is defined at any point in time. We can look at how is the distribution, how is the density at this point in time. And it could be, you have, say, n time points, n samples. And then how is the density of that? So it's just, say, if we are in the sum of Gaussians, we have a multivariate normal distributions. For the white noise signal, it's just a sequence for any value t that we can pick. We'll just have a standard normal distribution, and they will all be independent of one another. So then that one here will be quite simple. It's just a multivariate normal, standard normal distribution with uppercase sigma being a diagonal identity matrix. So we can pick the time points, we can pick how many observations that we have, and we call it the family of finite dimensional probability density functions. I won't ask you to repeat that, but that's what we call them. So it's the finite dimensional because we only take a sequence of n's, not an infinite sequence of observations. And then it's a probability density function. Well, that's kind of clear from the definition up there. So it's the finite dimensional thing that we just think of. As long as we're in discrete time, we're in a finite dimensional thing. If you go to continuous time, it's infinite. Because you can always, whenever you have a time interval, there's always, you can always put a sample in between. And this is a complete characterization of the stochastic process. It's not the way we want to go. It's the way we need to go in order to do something simpler in the long run. Just as I kind of said here, if we have white noise, we're basically just looking at some independent normal distributions. That's easy. So, we talked about this a long time ago, in your mind maybe, just a few weeks actually. Second order moment representation, what do we need? Do you recall? Well, you need the mean value. What else do you need? Yes? The variance, yes. One more thing. And the covariance, exactly. So you need the full covariance structure, which includes the variance. So the mean of a process or the expectation of xt, that's the integral defined as the expectation previously. Nothing new here, I would say. It's just, here we are for a given value of t. The autocovariance function, now you have a process. And I do not call it covariance as before. I call it auto. Does anyone know what auto actually means? Itself, exactly. So it's your covariance with yourself, which makes a lot of sense because then we're looking at, say, C0 here for the red one and say T1 over here. Then we're up there. So you're looking at the covariance between those two observations, or those 2 points in time if you're looking for the generic stochastic process. But it's with yourself. Within your realization, what is the covariance with yourself? And the definition is the same. You just have a look at the time point. It's the value or the distribution at time t minus the mean value, and likewise at time t2, sorry. So that's, and you can say the variance is, as usual, x minus mu square, the expectation of that. So that's so everything here is sort of the same way as what we did for the multivariate normal distribution. The only difference is that we're not looking at x and y, we're looking at x at different points in time. Or for the variance, it's at the same time. So that's the only difference here. But we will use the autocovariance structure quite a bit today. And now I got to a point here. I picked my old pointer here because I thought that the green dot was easy to see. In particular, on the video, you cannot see the red dot. So I'll see if you can actually see the green one. So someone looking at this, I mean, please write me an email if you can see the green dot in the lower right corner right now. Unfortunately, I have some signal problems with this one, but that's another story. Stationarity. You are indirectly asked to look at this in assignment 1. So a process xt is so-called strongly stationary if all finite dimensional distributions are invariant for changes in time. That means for any n and any set of time points, then it holds that if you take the finite distribution function from here and shift time by h, they are the same. The example down here, if you assume this is white noise, if you shift, then we have a normal, standard normal distribution here. If you shift time to somewhere else, you will again have a standard normal. So a standard normal distribution, it will have the same density no matter how you shift time. So a white noise signal, a white noise process is strongly stationary. Often we will just talk about weak stationarity of order k, where we'll just look at the first k moments and check if they are invariant to time. So to say of order 2, you need to look at whether the mean value is dependent on time and the covariance structure is dependent on time. And when we talk about weak stationary processes of order 2, we just call them weakly stationary, or often we just say stationary. Don't say strongly stationary, but just stationary. Well, in practice, we will mostly deal with Gaussian processes. If you look at the first moment and the second moment, then you covered the mean and the variance. If they are invariant to changes in time, what happens to any higher order moments? If you take higher order moments of a normal distribution, if the mean and variance are invariant, how many parameters does it take to describe? Yes? Yes, so there's nothing. So that means as long as the noise that we have here gives us a Gaussian process of some kind, then when we just look at the weakly stationary of order 2, it's actually also strongly stationary. But so that often we'll just look at the first and second order and say that's fine.
Can you repeat that? Why is it? Why does it?
Yeah, because if you look at the density here and assume that f is a density of a multivariate normal distribution, if the mean and covariance structure is invariant to changes in time, the density is invariant.
So you said if we have different distribution,
If you have something that's non-Gaussian, yeah, if you have, say, a gamma distribution or whatever, then you would have to look into higher order moments as well. So when things are stationary, we don't need to talk about mu as a function of time. We can just talk about the mean value. Likewise, the variance is supposed to be independent of time, and the autocovariance does no longer depend on T1 and T2. It only depends on the time difference between the two time points. And that's where we will spend the most of our time. That's when we have these assumptions are fulfilled. To have a process that is ergodic, well, usually, as I said a couple of times by now, you just have one realization, say the red one here. So that means that we will actually not know everything about the stochastic process, because we don't have a distribution at any point in time. We just have a point, one observation. So we need to say something about the distribution at any point in time. And if the process is so-called mean ergodic, then we have this, that we can look at the expectation of the process, not just the realization. So that is what we want to calculate. We want to look at the expectation, namely the integral over the sample space of x times f of the sample space. Now, what we can then do is to calculate this integral from minus t to t of x dt. So that is just calculating and divided by 2t. This here is just the mean value of the realizations in the neighborhood of t. Right? Sorry, for the given value of t that we want to look at. So what you go for is you do the integral over the entire time and say that is my mean value here. You do the integral across time. If that is equal to the mean value of the stochastic process here, then it's mean ergodic. It's not something we'll spend a lot of time on, but just so that you have the concept that from a single realization, if it is mean ergodic, you can actually say something about the structure. Yes?
Well, okay, now you said we're not going to spend a lot of time on it, but could you say a bit more about how you get from the left to the right integral?
This is actually the definition. I could have written a triple equal sign there. So the definition of, so you can say the definition of mean ergodic, this is the definition of the expectation till here, right? And then we say, if it is mean ergodic, this equals that.
Oh, okay.
So the last equal sign is if and only if.
Yeah.
And then if you want to know more, you can, there's a link down here. Just spend 5 minutes looking there, but I don't want to be reading it up or something like that. It's better for you to spend a few minutes doing that. I've said a lot about normal or Gaussian processes so far. And I also said that all finite dimensional distribution functions are multivariate normal distributions. That's where we want to be, because when we are there, a lot of things are easy. Another thing, for a process to be Markov means that the conditional distribution is only dependent on the latest state of the process. So there's no dependence. All the information that you need to predict what happens in the future is where are you right now. Say if you want to predict where I am in a second from now, all you need to know is where I am right now and maybe some information about my velocity. Then you have all the information that you need, but if you at any point in time know everything, you can predict. And you can say most physical processes are Markov by nature, but you need to figure out how much information to save in order to have that information. Say, if you do, for the example, figure out where I am, it's not sufficient to know where I am, but you also need to know my velocity to know where am I supposed to be in a second from now. So, if a process is fully deterministic, you can predict without any uncertainty if you just have some past values. If it is a pure stochastic process, then you can write it as an infinite, or potentially infinite, linear combination of uncorrelated random variables. And of course, what we usually observe is a combination of something deterministic and something stochastic. So you can take, at least for many processes, you can decompose it into a stochastic part and a deterministic part. And then you observe the combined thing. Okay, I kind of said this before. For a stationary process, the autocovariance and autocorrelation, haven't been there before, only depend on the difference in time. So rather than writing t2 minus t1, I will use tau as the difference in time. So the covariance structure, often I will, or sometimes I will write gamma subscript xx to say that it's x with itself. Reason being that we will also later introduce the so-called cross covariance between x and y, sort of like what we did for the multivariate setting. We look at the covariance with yourself, but you could also look at the covariance with something different, with another stochastic variable. So, the definition is as before, it's the covariance between xt and xt plus tau, and it's the expectation of the products. Now, I did one thing here. I omitted one thing. Can you see what that is? Yes? I'm missing exactly minus the mean value or the expectation of the process, both places there. Often, we will look at processes that has mean value of 0. So in that case, it doesn't matter. So most often, if we can just say that the mean value is 0, this is where we want to go. So that is just a little trick. Makes life a lot easier. As long as you can go to something that has mean value 0, life is just easier. So, and I will try to make life easy whenever I can. I hope you agree on that. The correlation is, as always, defined as the covariance divided by the variance. And the variance is the autocovariance lacks 0. Or we can also call it sigma square, as we have done. You can use that either way, but I would often use gamma of 0 as here. So gamma of tau divided by gamma of 0 gives you the correlation. So a couple of properties for the autocovariant. The first one is, well, if you go forward in time or backward in time, gives you the same thing. So does that make sense? By intuition? If we again look at what we have over here, if we look at tau forward in time, or look at tau backwards in time, let's call this distance here tau. Well, if you look at the covariance between this and that, is of course the same as the covariance of this and that. Right? Also, when we looked at the multivariate normal, if you flip the order, you transpose the matrix, but when you do it with yourself, it is a symmetric matrix. So those two, if you look at the diagonal here, those two elements, they will be the same. So that's the same reason here. Another thing is that the absolute value of the autocovariance will always be less than or equal to the variance of the process. Does that make sense? At first, maybe no, but then let's go to the autocorrelation. If, let's just assume, gamma of tau at some value can be greater than the variance, that would mean that this ratio here would be greater than 1. But the correlation is never greater than 1. Well, never outside the interval from -1 to 1. So per definition, if the last thing here was not fulfilled, we would have a problem. So, we are in a linear process. That's also where we'll spend most of our time. Now I wonder why this one is not updating. Weird. I was trying to see the live stream there because there's been some issues with the video. Sometimes things are missing. But that may be true now as well. Whatever, I'll check that later. So we will generally focus on linear processes. And that means that you can write a process, first subtract the mean value. Now you have a process with mean 0. Everything becomes nice. And then you can describe that as an infinite, potentially infinite sum of some epsilons that are independent with some weights psi I. So you have some white noise signal, uncorrelated, identically distributed, or independent as well. And without loss of, we can assume that psi 0 equals to 1, just to say that you can either choose that to be equal to 1 or to say that the variance of the epsilon is standard normal. But you cannot let both be free, then you cannot estimate it. Because you can just multiply the entire sequence of psi with a number and divide the variance or the standard deviation with the same number, and you get the same distribution. So you need to make a restriction on either the sequence of psi's or the variance of the epsilons. We will typically have psi 0 to be 1. That means that you will have epsilon of t with no factor on it. And we will just, again, without loss of generality, assume that mu is 0 for most practical purposes. Now, having this definition here, well, what did we do last week? What we did was to look at backward shift operators, among other things. So we have an infinite sum there of some process. We can make that an infinite sum like this. Notice here that I moved a 1 outside to say that psi 0 equals to 1. So I have a polynomial here, psi of b, that is this operator here. And if I apply that on epsilon, I get exactly what I have on the previous page. Likewise, if I have the process of this form, I can take this polynomial and invert it and pre-multiply it on yt instead. If the inverse exists, there's no guarantee that it will exist, but we'll get back to when you can do that and when you cannot do that. And now comes the, you can say, the tricky part for now. If you look at the autocovariance using psi weights, how do you get to this? What we have to look at for a given k, gamma of k equals the covariance of yt, yt plus k, just so that we kind of keep track of what we have. Then I will just write yt plus k. That is psi 0 times epsilon t plus k. That is a 1, but let's just write it right now. Plus, I can also remove it. Psi 1 on epsilon t plus k minus 1 plus dot 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 plus psi k epsilon t plus psi k plus 1 epsilon t minus 1 plus, and then to the end of time. If I then write yt down here, and I kind of collect yt starts with epsilon t. So I have an epsilon t here plus, and then I have psi 1 epsilon t minus 1, and then, of course, psi 2, epsilon t minus 2, and so forth all the way back. And now I know why I wanted to write the zeros here. So now, when I want to take the covariance between these two, what do I get out? All the epsilons are assumed to be independent. So there's no contribution from what you have here, but every term here, epsilon t with epsilon t gives a contribution, epsilon t minus 1 with t minus 1, and so forth. So the covariance up here, well, we have the covariance here. You have to take the two factors outside. So you have a psi 0 times psi k sigma epsilon square from this part here plus, and then I have a psi 1 times psi k plus 1 sigma epsilon square and so forth. And that is what is written right here, sigma epsilon square, and then you have the size with a lag of k in between, as we have here. So, we talked about stationarity before. Now we'll come with a slightly different way of defining it. Just a calculation to do that is different. But the definition of stationarity is the same. So we are now still in the linear processes. It's stationary if, now we define this operator polynomial here and we evaluate in Z instead of B. And we say if it converges for Z greater than 1. What does that mean? Well, it means that if the old observations here, or old values of epsilon t, if they are downweighted sufficiently fast, it converges. So if we forget the past sufficiently fast, it does converge. And likewise, the definition of invertibility, the ability to kind of move the whole polynomial or invert the polynomial, is similarly defined if the infinite sum of I 0 to infinity of pi I set to the minus I power, if that converges for Z greater than, an absolute value of Z greater than 1. And this means, if this is fulfilled, you can calculate epsilon t based on recent values of yt. Otherwise, you will need the infinite sequence. But what you saw when you did, say, local trend models or simple exponential smoothing is, with the lambdas that you've used, the weight goes very quickly to 0. Right? That's essentially similar to what we have here. Because if we go back a couple, no, here. Basically what we have here is, you look at the weight of the different previous observations. What is the value that you multiply on that? And when you do simple exponential smoothing, you just do an average of those. And that tail will go fast to 0 if lambda is different from 1. Or less than 1. Okay, oops. Good. So now we go for statistical models. This is, you can say, the core part is to make a model of all this. Now we just defined some properties. Now we need to kind of get to weigh how can we actually use those properties. So we have this yt, we can write it as an infinite sum of previous epsilons. That's all fine. But most of us have not observed anything with an infinite dimension. At least I haven't. In practice, you have a limited number of observations, say up to n. And now you have to find an infinite number of parameters, or the size, from n observations. Is that easy? At least there are many ways you can do that. There's no unique way, because you have so many degrees of freedom up there. You have an infinite number of degrees of freedom for the parameters you can estimate, but only n observations. So it's sort of like fitting a second-order polynomial to one observation. There are many ways you can do that, right? Well, except that it's an infinite polynomial that you're fitting here to n observations, but it's the same challenge. So what you should do is to somehow restrict the sequence to something that you can actually deal with. So the restriction that we will generally make in this course is the so-called MA, or moving average. I'll just write it up to have it as reference over here. So there we have yt equal to, it's a moving average, so it's the average of the previous observation, or previous errors. Epsilon t plus, called theta 1, epsilon t minus 1, plus theta 2, epsilon t minus 2, up to some point theta q, epsilon t minus q. So, those are the moving average parts. Now we have the so-called autoregressive models. Well, autoregression, auto means with yourself still, so regression on yourself. So what we need to look at is a process, we'll write it as yt plus phi 1 yt minus 1 plus as many points as we like, down to phi p yt minus p. Like that. And of course, we can also have a process where we both have an autoregressive part and a moving average part. Just write it up till we have it. Phi 1 yt minus 1 plus dot 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 plus phi p yt minus p equal to epsilon t plus theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 plus dot 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 plus theta q epsilon t minus q. So this is the family of processes that we will focus on, where we only have a finite number of parameters. And then we'll try to find a way, how can we estimate this? This is not the topic of today, but later. And as always, we'll assume that epsilon t is white noise. We can also write it as polynomials, like this. Polynomials in the backward shift operator, and just keeping the definition of b on xt shifts time to xt minus 1, and so forth. So this is the compact way of writing what is at the top there. Now, how about stationarity and invertibility? If you take a sum, a weighted sum of a limited number of past values, past errors, it is stationary. Because as long as the epsilons here are bounded, you cannot, by making a sum of those, it will always be stationary. As all the epsilons have the same distribution, You just have a sum of Gaussians. It's invertible if the roots of theta of Z inverse, before we used Z and not Z inverse, so here we say that they should be inside, all the roots should be inside the unit circle. So you take theta of Z inverse and find the roots, and if they are inside the unit circle, it's invertible. For the autoregressive process, this one down here, it's always invertible because it's already written as a finite sum of weights on the previous observations. But the stationarity is this definition the same. The roots of phi of Z inverse equal to 0, the root in that polynomial with respect to Z, all lie within the unit circle. And for the combined model, well, if the moving average part here is stationary, it's stationary. If the autoregressive part here is on its own invertible, then it is invertible. So you can look at the two different parts independently for that. Just a couple of examples here. If you look at the autocorrelation, which is basically what we will spend quite some time on next week, how do we get to that? Chalk. So for a moving average model of order 2, it could be the model that is defined up there. Let's write that model up. An MA2 model. We have yt equals to let's 1 plus 0.9 b plus 0.8 b square on epsilon t. So it depends on two previous values of epsilon t. So if we should look for the autocorrelation of this, how do we calculate that? We need to first look at the autocovariance and then take it from there. So if we start out with lag 0, gamma of 0 equals the covariance of yt and yt. Maybe just to have it on both forms up here, I'll write it equal to epsilon t plus 0.9 epsilon t minus 1 plus 0.8 epsilon t minus 2. So how do I calculate this? It's actually not that difficult. All I have to do is to just insert this. The trick is, when you have another process, where do you want to insert? Here, there, or both places? For the moving average processes, we will generally insert everywhere so we get epsilons out. Because when we have epsilons, we know that they're independent, and then life becomes easier, because then we only have to look at those that have the same time point. So it is the covariance of epsilon t plus 0.9 epsilon t minus 1 plus 0.8 epsilon t minus 2, comma, the same thing, epsilon t plus 0.9 epsilon t minus 1 plus 0.8 epsilon t minus 2. And if we look at this, Now, I think I will write it out here. What do we get? Well, every time we have a epsilon t with an epsilon t or the like, we get a sigma epsilon square. So I'll take that outside the parentheses already. Epsilon t with 1s in front gives me a 1. Epsilon t minus 1 with a 0.9 with epsilon t with a 0.9 gives me plus 0.9 square. And likewise, epsilon t minus 2 only give a contribution with t minus 2, epsilon t minus 2. So we have a plus 0.8 square. Now we do the same thing for gamma of 1. So it's the covariance of yt comma yt minus 1 or plus 1. Here I just choose minus 1, doesn't matter, because it's invariant plus and minus, right? And I will do the same thing. I will just insert what I have. It's the covariance of just write the whole thing here, epsilon t plus 0.9 epsilon t minus 1 plus 0.8 epsilon t minus 2, comma. And then I have to write this shifted one time backwards. So that will be yt minus 1 is epsilon t minus 1 plus 0.9 epsilon t minus 2 plus 0.8 epsilon t minus 3. And again, I will have a sigma epsilon square outside parentheses. And then I will look into, well, let me start with epsilon t. Is there anything with epsilon t on the right hand after the comma? No. Okay, so there's nothing from there. Then I have 0.9 times epsilon t minus 1. And I have a t minus 1 here. So that gives me the first number is 0.9. And then I have 0.8 times epsilon t minus 2. And I have epsilon t minus 2 over here with a factor of 0.9. So then I get 0.8 times 0.9. And then I don't have anything more here. So it doesn't matter that I have an epsilon t minus 3 here. There's no contribution. And if I do it again, shift it another time lag, gamma of 2 is the covariance of yt minus yt comma yt minus 2 equals the covariance. Do the whole thing again. Epsilon t plus 0.9 epsilon t minus 1 plus 0.8 epsilon t minus 2, comma. And then yt minus 2 is epsilon t minus 2 plus 0.9 epsilon t minus 3 plus 0.8 epsilon t minus 4. Again, I will have a sigma epsilon square outside a parenthesis here. And now I will do the same thing. Start from one end, epsilon t is not over here. Epsilon t minus 1 is not over here. Epsilon t minus 2 is here with a factor of 1. So I have a factor of 0.8 and a factor of 1. So that gives me 0.8. T minus 3 and t minus 4 are not on the first part, so there's nothing more. If I do it for k as a gamma greater than 2, I don't think I have to go through the whole calculation, but if I go for gamma of k for k greater than 2, what is the value? 0, exactly. So that's how to do That's what you need to do to make the graph there at the top. Well, actually what is left is now to take this one here and that value here and divide it by the variance that we got up here. So the sigmas goes out and we have this divided by that and 0.8 divided by that. That's the autocorrelation structure that is plotted up here. If we do the same thing for what I call an AR1 process like this, you can see that it's quite different what you get out. And the calculations also goes a little bit different. So what happens? For the AR1 process, which is kind of a classical example, we have 1 minus 0.8 b on yt equals epsilon t, which is the same as yt equals, and then have 0.8 b here. So that will be 0.8. Take the minus, becomes a plus when I move it to the right-hand side. And the b gives me yt minus 1 plus epsilon t. So that's the process. The procedure is somewhat the same as above. We start with the variance. And that is the covariance of yt, comma yt. So we'll just, in this case, insert on both sides as well. So we have the covariance of 0.8 yt minus 1 plus epsilon t, comma 0.8 yt minus 1 plus epsilon t. And here we have to think a little bit before giving the conclusion. When we have two terms, two elements here and two elements here, it's just like multiplying two parentheses together. So we take the first one with the first one, the first one with the second one with the first one, and so forth. So the first one with the first one, that gives us 0.8 square, and then I have yt minus 1 with yt minus 1. What is the covariance of my t minus 1, comma yt minus 1? It's invariant to changes in time. So it's the same as the covariance of yt and yt. So I will write gamma of 0. And then I have 0.8 yt minus 1 with epsilon t. Epsilon t is IID. So epsilon t is in the future relative to yt minus 1, right? So what is the covariance between 0.8 times yt minus 1 and epsilon t? Someone else? That is just 0, exactly. And likewise, the contribution from epsilon t with 0.8 and yt minus 1 is 0. So what is left is epsilon t with epsilon t, which is sigma epsilon square. Well, this is an equation in gamma of 0, right? So I can solve this. So what I'll do is to move this to the left-hand side. So then I have 1 minus 0.8 square gamma of 0 equals sigma epsilon square. And then I can solve, say, gamma of 0 equals sigma epsilon square divided by 1 minus 0.8 square. So here, yes? Here I have it as 1 times gamma 0, and here I have 0.8 square times gamma 0. So then I have the 1 here, and then I move the 0.8 square to the left-hand side. So it becomes a minus 0.8 square. Right? So what is next? Well, the next thing is that we do it for gamma of 1. And there we'll have a break in a moment. They're probably not too noisy out there. Otherwise, someone just close the door. YT covariance, and now I will take YT minus 1. What I will do now is a little bit different from what I did up there, and also here, because I will only insert the expression for YT once. So write it as 0.8 YT minus 1 plus epsilon t, and then I will keep the YT minus 1 here on the right-hand side. Because now I have a YT minus 1 and a YT minus 1 here. And we know the future epsilon has no covariance with the previous observation. So all I get out here is 0.8 times gamma of 0. And if I continue, gamma of 2, saving a little bit of time, I will go. I'll do the same approach as here. Covariance of YT, comma YT minus 2. I will insert in the first one here. It's a covariance of 0.8 YT minus 1 plus epsilon t, comma YT minus 2. Well, I'm not quite there yet, because I have YT minus 2 and I have YT minus 1 here. But I can take YT minus 1 and insert the value that I have for that. So I'll do that. It's the covariance of 0.8 times 0.8 YT minus 2 plus epsilon t minus 1, parenthesis close, plus the epsilon t from before, comma y2. Oh, sorry, t minus 2. And now you can see that the YT minus 2 does not have any relation to the future epsilon t minus 1, nor the epsilon t. The only thing that is this part here. So I get 0.8 square gamma of 0. And I hope you can accept that I will write gamma of k equals 0.8 to the k power gamma of 0. If I now divide by gamma of 0, I get the autocorrelation structure that is plotted here. So it's 0.8 square, cube, and so forth. And if we do a combined model, combining those two elements here, well, then we get something that after the initial part here is just an exponential decay, similar to what we see up here, but the first two lags up there are not, you can say, everything shifted a little bit due to the moving average part up there. And by definition, at lag 0, the correlation is always 1, because it's the correlation with yourself right now is per definition 1. I think now is the time for a break. So let's just resume. Oh, sorry, yes?
Could you elaborate a bit more on for the autocorrelation when y is yt minus 1 times epsilon t?
Sorry, why? Which one are you at?
Epsilon t times yt minus 1, when you do that part and say that's just 0, could you elaborate a bit?
Yes.
Why it's 0?
So this one here. So this is epsilon t. We get to epsilon t is only doing something to yt. It is not contributing anything to yt minus 1. So you get to epsilon. Epsilon t is independent of all the other epsilons. So it's independent of your previous observation. The future noise contribution is independent of previous observations. Your expectation of the noise in the future is 0. And then everything else comes from there. Yes, was there another question? Then have a break. We'll resume 12 minutes past.